Good morning, guys. In this video, we'll talk about a second method to solve the internal forces inside the truss, which is the method of sections. And we'll talk about the difference between the method of sections and the method of joints. But before going to the method of sections, guys, I want you to remember that in the truss, I only have forces on the joint. So I don't have any force on the member, any external force on the member itself, because if I have one member that has an external force, then this will not be a truss, it is a frame. Okay, so it is called a frame. And before going, guys, to the method of sections, I want you guys to remember how we did the method of joints. Basically, the method of joints is used in order to find all the internal forces inside the truss. And it is basically using the equilibrium equations of forces. So in the method of joints, I will not use any moment equation. So my only equations are the sum of fx and sum of fy for each joint. So for each joint, guys, I have two equations in the method of joints. And if I take this example right here, how many members do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 members, which means I have 11 internal forces. And in addition, I have two reactions at D and one reaction at the roller at E, which means I have 11 plus 3, 14 unknowns, 11 internal forces, and 3 reactions that are considered basically as external forces. Now, in order to solve for them, in the method of joints, I should take each joint separated from others, draw the free body diagram on them, and then find the internal forces by applying two equations per joint, sum of fx and sum of fy. So basically, guys, I should have a number of equations that is equal to the number of unknowns. I know that the number of unknowns in this example is 14. How many equations do I have? It is basically the number of joints times 2, because as we said, there is 2 equations per one joint. So how many equations do I have here? In fact, I have 1, 2, 3, 4, 5, 6, 7 joints, which means I have 14 equations, and I just said that I have 14 unknowns, so this truss could be solved. It is determinate. The number of equations is equal to the number of unknowns. I can go apply the method of joints, take each joint apart, and then apply the sum of fx, sum of phi, find the internal forces. In the method of joints, guys, I have to show the free body diagram of the joint itself. And then, guys, all the forces found using the method of joints are the forces applied on the joints, and they are not the forces applied on the members. My objective is to find the forces applied on the members, or the internal forces inside the members. So what I should do, whenever I know the forces applied on the joint, I should flip them, and these will be the forces applied on the members. But as a matter of fact, fortunately, if the forces were in tension on the joint, then these forces, even if I flip them, they will stay in tension on the members, and you can try it. Now the method of sections is totally different. In the method of sections, as its name, I should do a section or a cut. So I can call it the method of cut. Why? Because basically, guys, I apply the method of sections if the question is to find the internal forces in a certain number of members or in specified members. Which means, guys, if I go back to this example and the question is to find the internal force at BC, GC, and GF only. So it doesn't matter if you find the internal force in CD, FD, FE, AG, AB. My objective is to find the internal forces at BC, GC, and GF. So how to do this? I can, of course, go to the method of joints, find these forces, start by a joint that has the least number of unknowns, then go to the second joint, and so on until I can find all these internal forces. However, in the method of section, I can do a section that will allow me to show the internal forces. Remember, guys, the internal forces are internal. What does this mean? This means, guys, if I take a member BC, let's say this is the member BC, and if I do a cut on this member, I can see the internal forces. So, for example, these will be the internal forces. They are, of course, opposite. They are, of course, of the same magnitude. Because, in fact, they are internal, so they should be cancelled out. Now, if I cut BC and take the left side of BC, so let's say this is B and this is my cut, I will see this internal force. And if I take the right side, which is C cut, I will see also the opposite internal force. So that, guys, if I join them, these two internal forces will be cancelled out, and then I will have my member BC. So, guys, remember, these are internal. So if I do a cut, I will see my internal forces or the internal forces of the member. Now, basically, this is the concept of the method of sections. So the question is basically to find the internal forces inside BC, GC, GF. So what I should do, I should take a cut AA on these three members, separate them, separate these two parts, the left and right, and then comes the decision which part I should work on. Is it the left part or the right part? How to decide? This is in fact related to the number of unknowns in each part. So for example here, guys, if I take the left part, I only have three unknowns, which are the unknowns of the internal forces, FBC, FGC, and FGF. While if I take the right part, in addition to these three internal forces, I will have two reactions at D and the roller reaction at E. So I have 6 unknowns. So of course, guys, what I should do here is to take the left part. And then, since I have 3 unknowns, I should have 3 equations. What are these equations? These equations basically are the equilibrium equations, sum of fx, sum of fy, and the sum of moments. Unlike the method of joint, where the sum of moment will give me a trivial equation of 0 is equal to 0 because I'm doing the free body diagram at one point. Here, guys, the equation of moment is very important and relevant. Basically, from the equation of moment, I can get rid from 2 unknowns and find the third one. We will see how. So basically, guys, in the method of section, I should do an appropriate section that show me the internal forces that will be my unknowns, and I'm asked to find them. And I should decide which part I should take, and this is basically depending on the number of unknowns for each part. Now, how to decide what's the direction of the internal forces at this section? Basically, it doesn't matter. You can assume them. So like this case, guys, if I do this section here, I can assume that all my members are in tension. So I'm pulling out my members. But what's important, guys, is to put in your mind that in the other part, in the opposite part, in the right part, if I take the left, I will have opposite forces. But if F1 and F2 and F3 are in tension, of course, guys, F1 and F2 and F3 of the second part will be also in tension, but they are opposite. So that, guys, if I join these two parts together again, these forces that are internal will vanish. Now, how to assume their direction, it's up to you. So here, guys, in this example, I'm assuming them that they are all in tension. Now here, in this example, I'm assuming them that two of them are in tension and one is in compression, which is FGF. You can assume that they are all in compression. Now my method, like what I did in the method of joints, I will assume that they are all in tension, and then whenever I have a minus sign, then this means that this member is in compression. Now how to do my cut? It is basically, guys, any cut that can be useful for you. So you can see here different cuts, and you can of course do any cut you want, even if this cut is like this. As a matter of fact, guys, my cut should include all my internal forces that I need to find. Now what I want you to know, if for example I have the case where I should find the internal forces of these three members, like the problem that we will be solving in the following video. So basically, guys, I should do this cut. Because in fact, by doing this cut, I will show all my unknowns and all my forces that I need to find. And then, guys, by doing this cut, I will have two parts. One is left and one is right. So how to decide, guys, which part I should do? In fact, guys, if I take the left part, how many unknowns do I have? And remember, I only have three equations, sum of x, sum of fy, and sum of moments. I will have, this is the first unknown, this is the second unknown, and this is the third unknown, and two additional unknowns at the reactions. So I have 5 unknowns, 3 internal forces and 2 reactions at A. So I cannot, guys, solve for them. If I take the right side, I also have 3 internal forces, but I have another additional force here at D, which is the roller reaction. So I have 4 unknowns. So I cannot, guys, solve for these internal forces right now. What should I do? I should, guys, first of all, before doing any cut, take this whole free body diagram. This whole truss as my free body diagram. In this case, guys, there is no internal forces because I'm taking the whole truss as my free body diagram. So the only forces acting on this whole truss are the external forces that are the reactions. 1, 2, 3 reactions. So I only have 3 unknowns. I can apply the equations of equilibrium on the whole truss. I can find my 3 reactions, and then, guys, I can take the left or the right. It's up to you. Now, if you don't have a lot of time, what I can do basically is to only find the reaction at D by taking the sum of moments at A. So I can take the sum of moments at A for the whole truss, get rid from the reactions at A, find the roller reaction at D, and then take the right side, apply the sum of Fx, sum of Fy, and sum of moments on the right side of my section, find the internal forces. Or I can find all my reactions and then take the left side, because in fact, as you can see, in the left side, I don't have a lot of external forces like this right side. I have two external forces, 400 and 1200, and the reaction at D. So it's up to you. You can find the easiest way to find these internal forces. Let's now start by solving this problem.